Super. Okay. Thank you. Orthogonal projection is if you project a vector u onto V, the formula is u dot V divided by length square times vector V. All right. If you look at the book, another way to write it down is u dot V over V dot V. All right. This is precisely because you the length when you square it is exactly the inner product of the vector itself. Two things are equivalent. Okay, so so today we will be talking about cross product. So cross product, the similar things between cross product and the inner product is that they all take two vectors. Right? You still input two vectors. However, now the outputs, instead of a real number like in the product, you output another vector. So how does it work? So before we talk about cross product, so all of the concept we would like to introduce is called determinants. Actually, the cross product only makes sense in R3. Okay. Determinant. So if you have, let's say, a 2 by 2 matrix, right? The determinant is A times D minus B times C. So for example, if you have a 2 by 2 matrix, 4, 2, minus 1, 3, right? The determinant is 4 times 3, which is 12, minus 1 times 2, or minus 1 times 2 is minus 2, so 12 minus 2 gives you 14. So that is how you compute determinant for 2 by 2 matrix. For 3 by 3 matrix, it would be a little bit more complicated. So A11, A12, A13, A22, sorry, 21, 22, 23, 31, 32, 33. Right. So now you break it down into 3 components. So you took out A11, and then you delete the row and column associated with A11. So that is the 2 by 2 matrix formed by A22, A23, A32, A33. And then you multiply the determinant for this 2 by 2 matrix. So A11 times A22, A23, 32, 33. Right. And then next you move on to A12. You do the same thing. You delete the row and column associated with this A12, and then now you have A21, A23, A31, A33 left. So A12, A21, A23, A31, A33. However, the sign associated with A12 is no longer positive, so it's actually minus. So you have to put a minus sign there. All right. And finally, for A13, you do the same thing. The 2 by 2 matrix left is A21, A22, A31, A32. and the sign associated with A13 is positive. All right, and then you and after that, you basically break it down into finding determinant of 2 by 2 is well, you can expand it, but you get the idea, right? So for example, let's say you have a matrix 2, 1, 3 minus 1 minus 2 4 and 1 1 0, something like that. Okay, so the determinant by the formula is, first we take out A11, which is 2 in this case, and the 2 by 2 matrix left is minus 2 4 1 0. So 2 times minus 2 4 1 0. So for 1 here, the associated sign is minus, so it's minus 1 times minus 1 4 1 0 plus 3, right? The last one we do is the 3, so we delete the first row and third column. We have left with minus 1 minus 2 1 1. Okay, so for this 2 by 2 matrix, the determinant is minus 2 times 0 minus 1 times 4, so 0 minus 4. So this is 0 minus 4, which is minus 4. Okay, so for the second 2 by 2 determinant is minus 1 times 0. Oh, yes, sorry. Minus 1 times 0, which is 0, minus 1 times 4, which is 4. So this is 0 minus 4, which is minus 4. And the third one here is minus 1 times 1, minus 1 times minus 2. So it's minus 1 minus minus 2, which is positive 1. Oops. Okay. So the end result is 2 times minus 4 minus 1 times minus 4 plus 3 times 1 is minus 8 plus 4 plus 3, which is minus 1. Right? So far, so good. Okay, so why do we need to introduce the determinant is that the definition for cross products depends on the finding determinant. So let's say you have U and V are 3-dimensional vectors. Right? By the way, dot products only make sense in 3-dimensional vector spaces. Okay, so let's say that U is U1, U2, U3, V is V1, V2, V3. Okay. Then U cross V is exactly the determinant with the form that you put I, J, K vectors. Remember, these are the standard vectors in R3. Right? Basically, I only has information on X dimension, J is only had 1 in Y dimension, and K had only 1 at Z dimension.
Professor,
And the second row, yes.
Professor, is that the same thing as I hat, J hat, K hat? Is that the same thing?
Yeah, they are the same thing. You know, the book. Some books use hat, some books use both fonts. They all mean standard vectors. or standard
Right.
basics. Yeah. So reminder. I is 1 0 0. J is 0 1 0. And K is 0 0 1. Right. And the second row, you just put the vector u in the second row. So u1, u2, u3. Finally, and then you put v in this third row. So v1, v2, v3. So far, so good. And then you just compute the determinant for this matrix. So when you break it down, you do the same thing. You put you delete the row and column associated with vector I. You left with determinant of u2, u3, v2, v3 minus j u1, u3, v1, v3. Up. Okay, so plus k of u1, u2, v1, v2. Okay, so now you see why it returns a vector, right? Because when you do the 2 by 2 determinant, this is a number. This is a number. This is also a number. So you have number times a vector I. So this determines the x dimension. This number determines the y dimension, and this number determines the z dimension. All right. So that is the cross products, right? So there are some interesting properties about cross products. So right. I don't think it's a good idea to go into the reason why the algebraic properties hold. I think that requires some matrix algebra a prerequisite, which I don't think I want to go into detail. Right. So first of all, that the cross product is not symmetric. However, is actually anti-symmetric. So when you switch the order, you get the opposite. You get the negative, actually. Cross products. Right. Again, the reason is because the determinant is anti-symmetric. All right. The second one is that the
Professor, I have a question.
yes.
Where you said that the cross product, that's a u vector u and then vector v and then a u, you flipped it at the end.
That's how you get the negative sign. When you switch the order of cross products,
Okay.
you get the negative sign. So that's why I call it anti-symmetric. Right? If it's symmetric, that means when you switch the order, you get the same thing, right? What I call it anti-symmetric is that when you switch the order, you get the opposite vector. Right? When you negate a vector, right? When you have, let's say this is u cross v, when you negate a vector, you put it into the opposite direction. Make sense?
Yes, thank you.
Okay. They are still at the same line, but just put it in the two opposite direction. The second thing to notice is that the addition rule can the addition on one of the vector can be distributed like in the product. So you have U cross V, oh, sorry, U plus V. Crossing with W is the same thing as you cross it outside, add them up. All right. The proof, the idea is that when you have, you know, W1, W2, W3, right? Is that you can break it down into U1, U2, U3, and then W1, W2, W3 into two separate determinants, right? So again, that has to do with the property of determinants that I would just take it for granted, right? You will learn it in, you know, matrix algebra course or linear algebra course later on, right? Okay, right. Right. The third one can be actually, you know, is that the addition can be distributed in either one of the arguments. So the second one, well, let's put it, you know, to A and to B because these two are related, right? So basically, if you put the addition in the second argument, you can still distribute it. To see why is that, well, when you switch the order, you just, you know, trade it off with the minus sign, right? And then the argument flips to the first, the addition flips to the first argument, and then you can distribute it likewise by 2A. And then you just need to flip it on again because the order, you know, is, you know, you have to flip it back again, and then you trade it off with another minus sign. But 2 minus sign becomes a positive. So yeah.
Professor, just for clarification,
Right.
in the antisymmetric symbol, when you went the other direction, that cross product should be a negative V, right? Negative vector V.
Yeah. So this is a negative, right? No, the negative is on the outside. Well, I put the negative on the cross products itself, not on the V. So
on the cross product, yeah.
Yeah,
Okay,
like that.
so that's what the blue on the blue arrow on the figure that you draw. That's not negative.
Well, the blue is the negative on the whole green arrow.
Okay, so when I label it on the graph, I label it like that, or I put the negative sign.
Well, that's why it's a negative, right?
Yes.
It's a negative on my U cross V.
Okay. Yeah.
Right. Right. To write it down, why 2B holds is that, well, U cross V plus W. By rule number 1 is minus of V plus W cross U. And then by 2A, you can write it down as V cross U plus W cross U. And then you use 1 again. You just flipped U cross V cross U and W cross U to different order. So minus U cross V minus U cross W, the minus sign. And then you can distribute the minus sign there. That becomes minus of minus U cross V minus of minus U cross W. Well, 2 minus sign gives you back the positive sign. That's why it's U cross V plus U cross W. Like here. Okay. All right. Let me see if I'm missing something. Oh, the last thing is that about matrix, about a scalar multiplication is like in the product, you can distribute the alpha out of the inner product. Again, it has to do with the property of determinant. I would just take it for granted, all right? And sort of like rule number 0 is that if you have in the product 0, that tells you that if and only if U is U and V are parallel, or U or B or V is 0 vector. To see why is that, well, the second condition is sort of obvious. So when one of them is 0, right? So that means the whole row is 0. So that means these are 0. When you have a 2 by 2 matrix and then you have a 0 row, so you get 0 times anything is 0. So you have 0 minus 0, 0 minus 0, 0 minus 0. So you have 0i, 0j, 0k, so the end result is 0. So that means when you have either one of the row is 0, the cross product is 0. So that's why here means 0, right? And to see why the two vectors are parallel, is that if the two vectors are parallel, that means one of them is actually scalar multiplication of the other. All right, and then when you have well, one of the vector is scalar multiplication of the
Professor,
other.
are you writing something? Because I think that the screen is frozen.
Yes, the screen didn't move for us. We are.
Let me see. Sure. Is it moving?
Yep.
Okay. Okay. All right. So it becomes, well, by rule number 3, you can put out the alpha, right? So now you have a cross product of two vectors by itself. And you can see why that when you have a cross product of two vectors by itself, the end result is 0. Is that when you have, two vectors are the same, so that means or the v1, v2, oops. v1, v2, v3 are actually u1, u2, u3. So u2 times u3 minus u2 times u3 are 0, right? u1 times u3 minus u1 times u3 are 0. Same thing here. So you have the product of two exact same thing, and then they subtract with each other. So 0 here, 0 here, 0 here. So this is 0, right? And then the scalar multiplication alpha doesn't really matter. So because you apply any scalar to 0, still gives you back 0. So that's why if they are parallel, you get back 0. Right? And then that's if and only if, because there were no other scenarios that you can get a zero vector as a cross product. That's the only two options that you can give to get the result would gives you a zero vector from cross products. Right? So far, so good. All right. And how about special cases for cross products? What I mean by special cases is cross products on standard basis. Okay. So when you have I cross J, the result is actually vector K, right? There's sort of like a fun exercise you can do on your own. And J cross K gives you back I, and similarly K cross I is J. Right. Well, to get all the possible combination, right, you just switch the order. So K cross J is minus I, and then I cross K is minus J. Okay. So to better well, sort of like a figure of showing the relationship between I and J and K is that when you have I cross J, you get back K, and then when you have J cross K, you get back I. Right? If you switch the order like I cross K, you get back minus J because the arrow goes the other way. And then J cross I, you get back minus K because this the arrow goes the other way. Right?
Can you explain all that again? I didn't understand that.
So when you go from I to J, right, you should get K here. That's why the arrow goes here. But if you go,
I understand that part. Before that, like, why did you explain it? What do we need this for?
well, this is a cross product on standard basis. So you have basically when you cross product of two standard basis, you get back to the third one in R3. Right. This is sort of like you can verify it on your own. This is sort of like a small exercises, right, on manipulating determinants, right? You should get this on your own. The proof is sort of like exercise. This figure is sort of like a way of illustrating these properties. When you cross I and J, you get K. You just follow the arrow, right? If you didn't follow the arrow, you will get the minus. K cross J, you get minus I. Right. If you have I cross K, you go to the, you go against the arrow, you get minus. If you follow the arrow like J cross K, you get positive I. K cross I, you get positive J. This is sort of an illustration on this rules. Okay. So far so good. Okay. Okay. What's next? Like in the products, cross product also have interpretation. Cross product also have geometrical interpretations. So the geometric interpretation for cross product is that when you have vector u, and then you have vector v, the cross products actually is the vector that is perpendicular to both vector u and vector v. All right. So this is u cross v, right? So this cross product not only perpendicular to vector u, also perpendicular to vector v, right? So by that extent, because vector u and vector v can span a plane. So what do I mean is that when you look at vector u and vector v, they sit in a plane here. And then what do I mean by span the plane is that every point on this plane can be represented by a unique linear combination of u and v. So for example, I look at the point here. Well, the point can be taken as a small parallelogram formed by edges not by u and v exactly, but by a portion of u and a portion of v. So this is some portion of v, and this is some portion of u. Right? Because it's a parallelogram, this diagonal vector, diagonal edge is just the sum of the edges, right? And then you can, in fact, you can do it on all the points on this plane, right? It's this point, again, draw a parallelogram, a portion of u, a portion of v, right? Again, here, a portion of u, a portion of v. Furthermore, for the points along with the vector v, right? The parallelogram just becomes no u, right? Because this portion is collapsed onto the vector v, so there is actually no portion of u on the points here. Okay. So the plane is represented by the span of u and span of v. And the cross products is perpendicular to this plane P. Is everyone good with the concept of the plane spanned by u and v? I think this is a little bit of a hard concept to understand.
No, I need for you to explain that again.
Okay, so first of all, when you have two vectors, right, together, your intuition tells you that these two vectors have sort of like a plane that covers it. All right. What do I mean by there is a plane covers it is that when you span the when you have a point in this plane, right, you can always break it down into a parallelogram such that this edge, it lies on the vector u, and this edge lies on the vector v. This is a very important part to begin with. You good? Right. Sort of like from here, there is also a parallelogram. Do you see this picture?
Yes. So the components of the component of V, beta V, and the component of alpha U, they form the plane, right? Between these two vectors.
Right, because you can
Okay.
always change the value of alpha and beta, right?
Yeah, but are those like the components that formulate the plane? So like you know how like you have the X and Y components of like, let's say some arbitrary vector? Are those just the components that in essence create that plane?
Yes, because, well,
Okay.
alpha and beta can be anything. Yeah,
I see.
so basically, if you change alpha and then you get another point, if you change beta, you get another point. Basically, these are just variables, like a function on alpha and beta.
Oh, okay. And is this the reason why cross product can only work in R3? Like it can't work in any other um arbitrary
Sort
dimension?
of, because it is because it tells you about the perpendicular vector on the plane. So that's if you go to like R4, you lose the generality, because the perpendicular vectors may be more than one, because in R3 you have 4 dimensions, right? The perpendicular vector may lies in the 3rd dimension or the 4th dimension or something in between, and
right.
you don't get, there is no well-definedness. Basically, what is the vector you're referring to, right? But on R3, because there were only 3 dimensions, when you restrict the vector that is perpendicular to the plane, there is only one vector or one direction that you're referring to, right? There's no other direction that is still perpendicular to the plane. Does that make sense?
Yeah.
Yeah, so that's why the cross product only is well defined on R3 or any subspaces of R3. Basically, R2 also works fine, but in R2 is that the cross product only returns you to the z direction, right? You can see why, because when you have vector in the xy plane,
Right.
the
Yeah.
two vectors is only lives in xy plane, and the only vector perpendicular to xy plane is the z-axis.
Right. So you just end up with R3.
Yeah, you just end up
It
with
has
the
to
z.
exist in R3. Okay.
Yes.
What I'm
But
asking
for
is alpha and beta, are those scalars?
scalars, yes.
Okay, cool.
What do I mean by span of this is that the scalars can be anything. You take all possible combination of alpha and beta, all possible ones, right? When you do that, you take every possible linear combinations, and that's why this collection of points form a plane, right? Because there is no gaps in between, right? If there is no gap, that means you take every possible combination to fill this gap. Right?
Are you gonna give an example right now?
Yes, of course. So for, let's say u is 210, and v is, let's say minus 1, 1, 1. So U looks something like this. Okay, so this is U. V looks something like 1 minus 1. This one is somewhere here. 1 here. 1 here. So V is something here. You can see that the U lies on the XY plane here, and then V, sticks out onto the, imagine this is the XY plane is, Z-axis up. I have a, flat plane. Here is XY plane. So U is an arrow goes in this direction, and then V is going, sticking out of the board into, the direction I'm facing up. Okay. And the plane spanning the vector U and V, okay, looks like this. Okay. Well, actually, that's a bad idea. This is just making more confusion, right? To see that, you can see that, well, the U and V alone create an parallelogram by default, right? And this parallelogram is, you can imagine, is a portion of the plane, and then in order to get the whole plane, you just stretch this parallelogram along the edges of U and along the edges of V. If you stretch it along the edges of V, you get the point here, right? There's a long strips here. And then when you stretch the vector U, you get the points here, the short long strip here. And then when you stretch it together, you fill the gaps here, here, and here. So that's why you get the plane. That's why this span the planes U and V, of U and V. Does that make sense?
Yeah, it makes sense. But when you stretch it, that's what the scalars are for, correct?
That's the scalars for, right. That's
So
why
you
I
just
call
pick
it,
any scalars, or the scalars will be here.
because it's any scalar of alpha and any scalar of beta. When you do it like that, you span it. You take all possible points. Here, and here. All right. So for example, when you take alpha is equal to 1, beta is equal to -2, what do you get? Alpha U plus beta V is 1 times 2, 1, 0, minus 2 of minus 1, 1, 1. The result is 2 plus 2, 4, 1 minus 2, minus 1, 0 minus 2, minus 2. So the point is 4 minus 1 minus 2 is somewhere 4 minus 1 minus 2, right? So it's a point like here. Is you get it by you stretch U as by scalar 1, and then you stretch vector v by -2. You go to the other side. Okay.
Can you scroll down a little bit so I can get those notes?
So to draw the picture, imagine you have well, it's hard to imagine it in the 3 dimensions, so I put it back on the plane. So this is u and v, right? So in this case, the alpha u, well, the alpha is because it's only like 1, so this is alpha u, right? And the beta is -2, so you go to the other side by, and then you stretch it by twice, right? So the result is the point here. So this is on the plane because is formed by a parallelogram where the edges goes along with u and v respectively. So this is a stretch of the original parallelogram formed by u and v. Exactly. You stretch it down twice. You have the parallelogram, you stretch the edges down. And this is the parallelogram, the new parallelogram, alpha u plus beta v. Okay. And then you can do that for any alpha and any beta. You can stretch it any form you want, here, here, or here and there together. So you get the whole plane. Good.
Copy that, Professor. Copy that.
Why this is important is that now we can generalize a parametric equation on planes. Oops. So like the parametric equation on straight line, right? Straight line relies on you spanning a vector v into a straight line, and then you want this straight line to pass another line, so you shift it by another vector. So recall parametric equation on line is that you stretch or you span a vector v, and then you add another vector, so that, oops, I think the screen is frozen again. 1 second. Okay. Right. This is how we span a vector only once, right? And similarly with planes, right? You need to stretch a span vectors, right? But in this case, you stretching or spanning one vector is not enough, right? Like here, in order for you to have a plane, you need to span 2 vectors. Okay. Wait, hold on a second. Oh, sorry. Hold on a second. Scratch that. But for parametric equation on planes, you need two informations. First, you need a normal vector. So that is a vector perpendicular plane. Okay. And also you need to have a point on the plane so that because when you only have a normal vector, right? You have a plane, but this plane can move along the normal vector. So let's say this is your normal vector, right? When you only have a normal vector, this plane can work. But if you move this plane along the normal vector, right, you get infinitely many planes. So in order for you to be specific about the plane, you need to have a specific point on the plane. Let's say this x, or this point y, or this point z. Okay. How do we get the equation on the plane by using these two information? Is that when you observe, let's say if you have plane and then you have a point P on this plane, all right, then the normal vector the normal vector is perpendicular to any points or any vectors on the plane. So when you have, let's say this vector, right? So when you move along the vector so that it starts on the point P, right? So this is the same vector, only the position is changed. So because these two vectors are perpendicular, right? So that means n is perpendicular to v. Well, what do we know about perpendicular vector is that the inner product is 0. Right? So that works on any vectors on the plane. So in particular, particularly works on any vectors that start with the point P. So we only consider the well, is enough to consider the vectors that start with the point P. So let's say you have a point in the plane x, y, z. So we want to know what x and y and z represented. What can we express x and y and z with? The information we have, which is the normal vector and the point P. So let's say the point P has the coordinate x0, y0, and z0. All right. So first of all, what is the vector v? how can we express vector v? Vector v is the vector joining point P and this particular or arbitrary points x, y, and z, right? So the vector joining 2 points is, let's say this is vector x, is x minus p, because we start with the point P, so x minus p. So this is x minus x0, y minus y0, z minus z0.
What does vector u represent?
What is vector u?
Oh no, that's a v. Okay, sorry about that. I thought that was a u.
Okay. Z0. Okay, and another information we know is this part. Right? So we know that the inner product has to be equal to 0. So let's say we represent the vector n, the normal vector n is A, B, and C. That means that A and B and C dotted with x minus x0, y minus y0, z minus z0 is 0. Okay, and that means A times x minus x0 plus B minus B times y0 plus C times Z minus Z0 is 0. So you have an equation on x and y and z such that ax plus by plus cz is equal to ax0 plus by0 plus cz0. Okay. The textbook summarize this portion, right, with a number d, well, in the symbol d. So d, where is ax0 plus by0 plus c0, so that ax plus by plus, well, actually is minus part, minus of it, such that you have ax plus by plus cz plus d equals to 0. This is another way of writing the equation on the plane when you're given with a normal vector and a specific point on the plane. Okay, so with normal vector and the point of the plane, you can get an equation on the plane with these two informations. So for example,
I
But I
think
think
the,
it's frozen again.
yeah,
it's frozen again. Oh, sorry about that. All right. So for example, when you have a normal vector is
Hold on, Professor. Before you continue, the highlighted part, explain that again. How did you get ax plus by plus cz plus d equals 0?
which part?
The highlighted part in the yellow and red.
Yellow and red. So first of all, do you understand the red part?
No.
All right. So the red
Hold
part.
on, hold on. The red part is you basically just distributed the a to everything.
Yeah, that's how the inner product works, right?
Right, right.
B times this, C times this. Right. So this comes from the inner products of these two vectors. You good?
Yes, yes.
Okay. So, well, from here to the red part is you distribute the parentheses. Right. So you have AX minus A times X0, BY minus BY0, CZ minus C0. Okay. So I put the minus part all minus part to the right hand side. So the
Yeah.
minus sign becomes positive. X0, BY0, CZ0. Good.
Yes.
Okay. So from the red and the yellow is just another way of writing the equation. So
But where did you get the D from?
so the D is
Pause.
that's the how the book like to write the equation. Essentially, these
Okay.
two are the same. It's another way of writing down the equation. So the book put the red part as the D with the minus sign, so that you can write the equation in this form. You see that?
Yes.
Oh, okay, okay. So well, this form is a nicer way of writing this because there's too many symbols, but the idea are the same. So for example, if you have a normal vector 1 minus 1 1 and it passed the point 0 1 0, so the geometrically the point P is the point, well, this is the J vector, right? So this point P lies in here. What is the normal vector? The normal vector is 1 minus 1 1 and is 1 minus 1 minus 1 and 1. So, huh?
It was frozen for a second, but I think it's back.
It's not frozen, right?
It's
Is it?
not frozen.
Okay. Is 1 minus 1 1, so it points to somewhere here. Is it no, it points somewhere here. Somewhere here. This is the normal vector. And okay, so when you have the picture like this, the plane should look like this, right? So to sum it up is that this is the plane that we want to formulate where the point P lies in here and the normal vector is here. The normal vector sticks out of the plane to the left-hand side. Sort of hard to see. By this formula, right, we just formulated the plane is governed by the equation ax plus by plus cz plus d equals to 0. right? Well, what is A? A is 1. So this is 1. What is B? B is -1. What is C? C is 1. What is D in this case? D is AX0 plus BY0 plus CZ0. So is what is X0 is 0. So this is 0. BY0 is -1 times 1, so -1 plus 0. This is -1. Well, there's a minus sign of all of it. So this is +1. Okay. So you get D is 1. So to simplify it is all the x, y, and z such that x minus y plus z plus 1 is 0. All right,
Can you go back again and can you go back just a little bit more, a little bit up?
more.
So the XYZ represents the point.
X, y, and z means that you're taking arbitrary points in in R3. Right, arbitrary
Right.
point in R3 looks like x, y, and z.
So the A, B, and C, you just plugged in the points from the normal vector.
Normal vector, exactly. A and
Right.
B and C. This is x0, y0, and z0. The reason why the equation is there is that you cannot take any arbitrary point in R3 and throw it in, and then say that that point belongs to the plane. Right? That's not the case because the plane is only a portion of R3. Right? So to see what points fit in the plane is that you have the point has to satisfy this equation, as we showed earlier. All right. So this is the equation that the point x, y, and z has to follow. Right? And this equation you can formulate it by a, b, and c, and x0, y0, and z0 using the formula before. Is that x minus y plus z plus 1 is equal to 0. This is how the formula works. And then this equation tells you that in order for the point x, y, and z to be on the plane, you have to satisfy this equation. Right? So you can randomly, you can check whether or not a points are on the, whether or not the points on the plane. No. Right. Point number 1. Let's say you have 2 minus 1, 3. Let's check. When you put the point x, y, and z into the left-hand side, what it becomes is 2 minus 1 plus 3 plus 1, which is 2 plus 1 plus 3 plus 1, you get 7. On the left-hand side, you get 7. On the right-hand side, you get 0. So you can see. Yes.
-1 and 3. How did you get that?
What do you mean by how did I get?
How did you find P?
Well, in this case, we want to check whether or not the points are on the plane, right? I pick the point in R3, and then let's see whether or not this point is on the plane.
Okay.
Right? The point is only on the plane if it satisfies the equation. That's the important part, right? Any questions?
So we're trying to find the appropriate, so this equation it represents the plane, right? And you're just, yeah. And so the equation follows from the fact that we're using the inner product, and because the normal vector is 90 degrees away from the thing, from that plane, then like that's like a confirmation to say that, yeah, this is the correct equation for the plane.
Exactly. Right.
Okay.
You get this equation from the fact that the normal vector is perpendicular, and perpendicular means inner product 0. After you get that equation, this equation represents the plane in a way that in order for the points to be on the plane, it has to satisfy this equation. If it doesn't satisfy, that means it's not on the plane. If it's satisfied, that means it's on the plane. Right? It's
Yes.
infinite only if.
Yes, yes.
So-
So it has to work both ways.
Yeah,
So
point on the plane. Let me write it down. On the plane is equivalent is that XYZ satisfy the equation. Okay. So now for the job here is to check whether or not the point on the plane. So is the only way to do that is to check whether or not it satisfies the equation. Right? So in point 1, you have x and y and z with 2, -1, and 3, right? To check whether or not this is a fits the equation, let's plug it in into the left-hand side, right? Where you only have x, y, and z here. The left-hand side gives you back 7, which is not equals to the right-hand side. So for point 1, the left-hand side is not equal to the right-hand side. So that tells you that the equation is not satisfied.
Professor, I have a question.
Mhm.
We're talking about the formula up there. So the X, Y, Z, that's a equal sign or is that a minus sign? Is it equal to
Here?
X minus, no, on top? Is it equal to X minus Z plus, I mean, X minus Y plus Z?
Yeah.
So X comma Y comma Z, is that a subtraction sign or equal sign up there?
Here.
Over, one more.
Over.
No, over, you was right on the line.
Over on the line. Here.
No, where you was just pointing at, the X comma Y comma Z at the bottom of the screen.
This is a comma. It tells you that in order for
Is it
this
equal
x, y,
sign?
z to be on the plane, you have to satisfy this equation.
Okay, someone answered my question in the chat, so thank you.
Okay. Oops. Well, this is let me highlight it so that it tells you this how you get the number D, right? Okay, let's check another points. Now how about 2, 1, and actually 2 minus 1 and -4. Right. So in this case, when you plug this new set of x, y, and z, x is equal to 2, y is equal to -1, z is equal to -4. Into this equation, you get 2 minus -1 plus -4 plus 1. The math should gives you back 0.
Professor, so you're just randomly picking numbers.
Not exactly, but I'm picking numbers. Right. So in this particular example, the left-hand side is equal to right-hand side. That tells you that the equation is satisfied. So for the last example, equation not satisfied. That means not on the plane. For the second example, the equation is satisfied. It means that is actually on the plane. Okay, so far so good.
Yes.
The second way of finding the equation is that sometimes you're not given the normal vector. So in the second case, if you have the information that you're given 3 distinct points on the plane, it turns out is enough for you to find the equation for the plane as well. Okay, so the idea is that when you have 3 points, P1, P2, P3. Okay, so let's focus on P1. You can join the point P1 and P2 with the vector. This is, let's call this vector U. Do the same thing. You have a vector V joining P1 and P3. So U is P2 minus P1. V is P3 minus P1. And with 2 vectors, in order for you to get the normal vector, remember cross product is the way to do that. Cross product gives you back the perpendicular vector. Okay. So U cross V is the normal vector you're looking for. So now you go back, this gives you back to the part where you have a normal vector and a point. So a normal vector, let's say you picked the point P1 to be the point it goes through. Actually, you can pick any P as you want, P2 or P3. Since now you have a normal vector and the point, so now it goes back to the first step when you have A and B and C and P1 x0 y0 0. Okay, so for example, when you have U is, what is the U that I did? 210. Let's say you have now P1 is 0, 0, 0 is the origin. P2 is 1, 1, 1. P3 is minus 1, 1, minus 1. Okay, to make it simpler. So in this case, the U vector is the vector joining P1 and P2 is 1, 1, 1. Your vector V is minus 1, 1, and minus 1. And how do you compute the normal vector, which is the cross product of U cross V? Right. Is I, J, K, 1, 1, 1, minus 1, 1, minus 1. So in this case, you get 1, 1, 1 minus 1 I minus 1, 1 minus 1 minus 1 j plus 1, 1 minus 1, 1 k. So this gives you back 1 minus times minus 1 is minus 1, minus 1 times 1. So it's minus 1 minus 1, which is minus 2. Right, this gives you 1 times minus 1, minus 1 times minus 1. So this is 0. This gives you 2. Okay. So the result is minus 2i plus 2k. This is minus 1, 2, 0, 2. This is the normal vector. And then you picked the point P, P1 to be the point that the plane intersects or the plane lies on. So you have P is equals to the set of collection, the set of points x, y, and z, such that it satisfies the equation ax plus y plus cz plus d equals to 0. Oops. Right, where your a is minus 2, b is 0, c is 2. Right, these are from the normal vector, and the d is ax0 plus by0 plus cz0. There's a minus sign. So this is minus, well, x0, y0, c0, they're all 0. So this is 0, this is 0. Okay. So what, after you simplify this, it becomes the equation of minus 2x plus 2z equal to 0. Well, the 2 can be, factor out. So it becomes x equal to z.
And Professor, for example, like in a standard problem, they'll tell you which point to use as the basis for formulating the plane, correct? Because you just chose P1 arbitrarily, I'm guessing.
Yeah, arbitrarily. Yeah, because
Okay.
I feel like P1 is
The
has
easiest, yeah.
yeah, the easiest. Yeah, they're all 0. The computation
Yeah.
would be less complicated, but in other cases you can pick any P so that it you feel like is the most convenient to use.
Oh, I see. So it's up to the.
Up to you.
Okay. All right. Cool.
Right? Because remember, all these 3 points lie in the plane,
Oh, right. Yes.
right? So that's why you can
Okay.
pick any point you want.
That makes sense.
Okay, so what does this plane look like? Right? Because in this case, you only need to have x equal to z. The y component doesn't have any restriction. So the y can be anything on the y-axis. Here, you just need to make sure the x is equal to z. So when you draw it, when you look at it in the xz plane, you have the line z equal to x. What does it look like? Z equal to x is this. Right. So you just the picture would look like this. Actually,
How did you come to the conclusion of x equals z though?
yeah, x equal to what's that?
How did you come to that conclusion? Can you just do the red
Well,
part again?
Well, when you simplify this, where a is minus 2, right? So minus 2x. B is equal to 0. So this is 0.
Right.
Plus 2z. What is d? D is also 0.
Yes.
All right. So that means is x equal to minus 2x plus 2z equal to 0. Right. So when you move around, 2x equal to 2z divided by 2 on both sides, x equal to z. Okay. So x equal to z, this line, this is the well, when y equal to 0, when you only look at the xz plane, x equal to z is a straight line look like this, but the y is anything we want, so we just span this line on along the y-axis, so it looks like this. Right, so this is the plane on imagine, well, it's really hard to imagine. You have your z-axis. Let's suppose your z-axis this side, and then your x-axis is going on my left. The normal plane is this part that is like 45 angle along this between these two sides. You see that? It's a little bit hard to imagine on R3, but that's how the picture looked like. All right. I think we're a little bit running out of time. The next thing I want to talk about is that the inner product related to the side of the vectors. So when you have vector u, vector v, the angle between the two vectors is theta, right? You form a parallelogram using edges of v and u. This is parallelogram. Right. The u, the cross product is also related to the parallelogram in the way that the absolute, the norm of the inner product. Remember the inner product. The norm of the cross product. Remember, cross product returns you to a vector. Right? The vector has norm. The norm is actually equals to the area of the parallelogram. All right. So this gives you a way to calculate the area of a triangle in R3. All right. So for example, you have P1, P2, and P3. Again, using similar ideas, you get a vector u and a vector v. All right. By joining P1, P3, and P1, P2, right? So after you get the vectors, you can form a parallelogram, right? Remember, a parallelogram, the area of the parallelogram is the double of the triangles, right? Because this part of the triangle and this part of triangles are actually congruent. Remember, this is some basic geometries. All right. So because their congruent area is the same, so the parallelogram is double the size of the triangle that we want. Right. The triangle of P1, P2, P3 has the area is less the 1/2 of the area of the parallelogram And how do we get the area of parallelogram? It is precisely the norm of U cross V. Okay, so go back to the last example when you have P1, P2, and P3 here. What does it look like in 3 dimensions? So this is P1, is the origin. P2 is somewhere on the hard to draw it. P1, P2 is something stick out. Right? And P3 is something that on the back down here on the back down. So imagine again, this is the what do you call it, the YZ plane, right? This side is YZ plane. This side is the XY plane, right? Imagine this point is the origin we're talking about. The P1 lies in somewhere here. So the vector is V is here. And another point P3 lies in somewhere here. Is going down the other way. I'm sorry, going down this way. All right. Right. So this triangle is something here. How do we compute the area of this triangle? So the area of this triangle is half of the size of the area of the parallelogram, and the area of the parallelogram is actually the norm of vector U cross vector V. And we already compute what is vector U cross vector V is -2, 0, 2. So is half of the size of the length of the vector -2, 0, 2. Well, the length has, well, to compute the length of the vector is use the formula square root of -2 square plus 0 square plus 2 square. Right, so half of the size of square root of 4 plus 4. So is half of the square root of 8, which is 2 radical 2. Well, when you half of it is radical 2. You can see why is the case is that well, the size here, well, is 0, 0, 0, 1, 1, 1, so it has a the length radical 3. This is also radical 3, and the angle in between of them, well, it's really hard to imagine what the triangle look like, but yeah, that's how we compute the area of this triangle. Okay. Okay. Another geometric interpretation of the cross product is that the cross product with is related with the angle between the two vectors. Is related to the angle between vectors. So again, the picture is like this. U and V with the angle theta is that the norm of the cross product is the same as the norm of U times the norm of V. And in this case, it times the absolute value of sine theta. All right. And if you notice that when you have two vectors, the normal vector may have two directions, right? It can go to upside to the upside. Imagine this is the plane. You can go up of the plane, or you can go downwards. How do we decide which normal vector are we referring to? Right. So this is what we call the right-hand rule. The right-hand rule tells us that if we start with the U, right, because we're talking about U cross V, so we start with U, and then your index finger goes to the direction of V, right, such that the angle between these two vectors is less than 180 degrees. So this is the angle. So now your thumb would point to the direction of the normal vector, which is the direction of U cross V. So again, here, U, V, and then U cross V. So in this case, let's put this as U, V. So U cross V is the red direction. Okay, and the blue one is precisely V cross U because the anti-symmetric. Right. Okay, there is only 10 minutes left. I'm not sure I can finish this topic. Is the distance from the point to a plane. So let me try. If I cannot finish it, I would put it to the next week. Okay. So the background here is that we start with a plane. Remember, plane, we can represent it by an equation, ax plus by plus cz. Oops. Plus d equals to 0, right? And then we have a random point. Let's say point P is x, y, z in R3. Right? We want to determine the distance between the point P. Well, it's too very confusion. Let's put the point. Use letter Q. Right? The point Q to the plane P. How do we determine the distance between the point to the plane? is that you need to find the normal vector between the point Q and the point P, right? Because the distance is the smallest length that such that the Q from the point Q travels to the plane, right? So if you travel in this direction, this is the distance. In another direction, right? Can be here, can be here, can be here, right? And it turns out the smallest distance to travel is the one when you have the perpendicular direction. Okay, so that's why we need to find the normal vector. All right, and the normal vector to the plane P, right? By this formula, right, we know that the normal vector has it looks like this, right? Okay, and then so the normal vector, right? And we need to we want the distance between Q and the plane, so that means we want to have a portion of the normal vector, right? Because normal vector goes from a point, let's say this is the point x0, y0, z0, right? Oh, what do I want to say? Is that this normal vector does not necessarily goes to the point Q. So the picture I have in mind is that this is the normal vector that it lies on the point x0, y0, z0, but the Q is outside of this normal vector, right? So in order for us to have the projection, right, because the distance, I'm sorry, the distance here, right? One way to look at that is to look at this particular parallelogram.
Are you drawing on it? Because I think you're frozen again.
Froze again? Let me see.
'Cause I can't. If you're writing, I can't.
Give me 1 second. We good? Okay, so this is the picture I have, not necessarily I have in mind though, because the Q may be, you know, way up than the normal vector n. Okay, so in order for us to have the distance, this is the distance we want, right? We need to well, this is the, let's say this is the vector joining x0, y0, z0 to the point Q, right? The distance is precisely the orthogonal projection onto the vector n. Okay. So what is this vector joining the point? Let's say the point on the P is say x0. Oh, sorry, too many x's. Q0, sorry. The point from point Q0 on the plane to the point Q, right? We can always find the vector joining this 2 point, right? So let's use the red line representing the vector Q0Q. So vector Q0Q is Q minus Q0, it's x minus x0, y minus y0, z minus z0. Let's avoid some confusion. Instead of using x, y, and z, it doesn't mean it's arbitrary. The q is actually given. X1, y1, z1. So this is x1, y1, z1. Okay. And the distance is precisely the orthogonal projection. Is equal to the projection, orthogonal projection of the your vector Q0Q onto the normal vector. The picture is like this. You project the red on the normal vector, so that this is the distance. Because the distance that needs to be perpendicular. The distance vector needs to be perpendicular. So you need to project the non-perpendicular vector Q0Q, the red one, onto the blue one, so that it becomes perpendicular. That's the orthogonal projection, right? This power of orthogonal projection. So this is Q0Q dotted with the normal vector n divided by the norm of normal vector n square times the normal vector n. This is a distance vector. We just need to compute the norm of this distance vector. So just need to compute the norm of this projection. Well, the norm of this projection is the norm of this vector. Remember, this part is a scalar. You can always put it out. So absolute value of the scalar divided by the norm n square times the norm of n here. Well, this part can be canceled out with ones. So this is absolute value of Q0Q dot normal vector n divided by the norm of the normal vector n. All right. To write it down explicitly, Q0Q is x2 minus x1, y2 minus y1, z2 minus z1, dotted with a, b, and c. What is the norm of n is square root of a square plus b square plus c square. All right. So the dot product, well, you have the absolute value. All right. The dot product on the numerator, right? You just distribute a, b, c. That's the dot product. So a of x2 minus x1 plus b of y2 minus y1 plus c of z2 minus z1. divided by square root of a squared plus b squared plus c squared. Well, there's one more thing we need to do is that, well, the x1, y1, z1 are not given. We don't know what point it goes to. However, what we know is the area, the equation ax plus by plus cz plus d equals to 0. That is the equation of the plane, right? What is the d in this case? D is equals to minus ax0 by0 cz0, right? So if x0, y0, z0 is on the plane, D looks like this. Or in this case, x1, y1, z1. So x1, y1, and z1. So when you distribute the top part, you have ax2 plus by2 plus cz2 minus ax1 minus by1 and then minus cz0. The part where you have all the minus is precisely the same as D. Okay. So this is equals to ax2 plus by2 plus cz2 plus d divided by square root of a squared plus b squared plus c squared.
I think it froze again.
Okay. So this is the equation, well, formula of finding the distance from a point to a plane. So the point, remember, point has the coordinates x2, y2, z2. The plane is x, y, z. Such that it's governed by the equation ax plus by plus cz plus d equals to 0. So you know, so the A, B, C, D are given, x2, y2, z2 are given. Right? We're running out of time. Let's do the example next week. You can start trying solving some questions on the homework. I think 1 or 2 questions are related to this part. All right. Any questions so far?
I don't have any questions.
So let's see what homework questions I assigned. 6, 13. 6. B 16C.
These questions are at the end of the chapter, correct?
No, this is end of the section.
End of the section, excuse me, yes, right.
Yeah. Does not have the one that computes the distance from a point to the plane. Let's throw in question 34. Yep. Okay. So question 34 asks you to compute, find the distance from a point to a plane. Right? So it's a good exercise on the last topic. Again, I will do the recap next week so that you can better understand how to use this formula. But yeah.
So the orthogonal projection comes from trying to map that vector we constructed onto the vector normal, correct? That's why we're using it. I'm just
Which
trying
one?
to understand.
Yeah,
So yeah,
yeah,
so we
go ahead.
construct Q and Q sub 0. We construct that vector, and then we wanna find the distance. So we use the orthogonal of that onto n, right?
Yes. Yeah, because Q0Q may not be orthogonal, right? How to make sure is always orthogonal is that we project this
I
part
see.
to the normal vector so that it becomes orthogonal.
Because that's the shortest distances.
It's the shortest distance, right? Because if you project it out away,
Oh, I
you
see.
get longer one or shorter
Yes.
one. The orthogonal
Okay.
projection is precisely the one we want.
Yes, okay, I see it clearly. All right, thank you.
No problem. Another way to see why you need the orthogonal projection is that when you look at the parallelogram, right? Because normal vector is always perpendicular to any vector, so you have to have a orthogonal projection because this vector, this angle, needs to be a right triangle, needs to be perpendicular. So you are forced to have a orthogonal projection if you want to find the distance. Right? Okay, any questions so far?
No, sir.
I guess I will see you next week. Have a good weekend, everybody.
All right, thank you,
Bye.
Professor.
Good,
Bye.
Professor.
Take care.
Take care.
Bye.